So thank you, Ulysses, and thanks everybody for coming. I know how hard it is to come on the last day, the first lecture in the morning. When I was in your position, I actually always felt bad for the person in my place now, to being the first in the morning on the last day, but yeah, it is what it is. So let's get started because, well, as you might have noticed, I'm still late with everything, but I prefer to try to do things well instead of giving you a lot of information that is not connected. So I'm going to continue with the cosmic ray transport part that we started yesterday. And then, if I have time, I didn't talk too much about observations. I'm giving you a lot of theory because I find that this is a bit lacking in schools, like the very theoretical background building up slowly. That's why I decided to do it. So I'm going to do this if I have a bit of time. But yeah, now we are going to focus on the cosmic ray transports that we started yesterday. So if you recall, yesterday, we did a very simple case. We started with a magnetic field. We had this case 1, that I call this case 1, which was a homogeneous magnetic field. Right, and then I said that the magnetic field, I just defined this and I derived a bunch of equations. This was very easy to do, basic electromagnetism, everybody was happy. Then I went to the second case. In the second case, I introduced an inhomogeneous magnetic field. And I define this inhomogeneous magnetic field as, well, this simple homogeneous magnetic field plus a perturbation. And this perturbation, well, this is in the plane perpendicular to the z direction, okay? Just by definition to make things simple. Because otherwise, you can just absorb this definition into the z component. So this is a very useful thing to do. Okay, so case 1, very simple, everybody knows how to do. We get that the motion of a particle, if you just solve the Lorentz force equation, it's going to be helical. It's going to be like a circle with a fixed radius moving in one direction. That's the first case. In the second case, you would have this, but it would start to be tilted, the radius would change a bit, and this is what we talked about. And why am I building things in this way? Because here, when we add the perturbation, we need to understand the physical, the astrophysical, actually, motivation for that. And the astrophysical motivation for that is turbulence. Magnetic fields in the universe, they are turbulent. There is a bunch of things going on, plasma processes, and I, of course, don't have time to go into that, and I don't know enough for that. So usually plasma people, they devote their whole career for that, so it's not something that I did. But yeah, so here it's where plasma processes in this turbulent media starts to become important. And these processes, like in this case, you have a turbulent magnetic field with all these plasma processes, and they create a distribution of magnetic fields, which is kind of, seems a bit random in some sense. I'm going to show you a few examples. But before that, in this inhomogeneous magnetic field, when I say turbulent, we need to define what is a turbulence. And what is a turbulence? Well, to be honest, it's something that I did not know. I worked with magnetic fields for many years, and until like I had to teach this for the first time, I did not know how to define a magnetic field, like a turbulent magnetic field. I kind of had a feeling, but I had not formalized all of this in my mind, but now it became clear, or I hope so. So what's, actually I'm calling this a stochastic magnetic field, and they are almost the same thing, not exactly, but very close. There is a superposition of components, and we usually describe this magnetic field, turbulent or inhomogeneous magnetic field, in Fourier space. So we take, okay. When we do it, that's why there is a case somewhere here. We just decompose this magnetic field in a given, in the Fourier space, like in a given K space, right? And we define this thing here, which is very important, that's called the power spectrum of the magnetic field. The power spectrum of the magnetic field, in this case, I'm defining as a power law. Like many things in nature, it's a power law. It's very simple and intuitive. So it's a power law. It has like an index alpha b, which is I'm calling the spectrum index, but it depends on how you define it. You could call alpha b, what I'm calling alpha b minus 1. But anyways, and what's this power spectrum, which is defined again in Fourier space? Take a look at this plot. So I'm changing here alpha b. So we have alpha b equals to 2, alpha b equals to 0. So if this value starts to become more negative, it means that your power law, so like minus 3 here, so we have minus 4. It means that your power law is favoring the smallest k values. And in Fourier space, small k means large scales. That's this one. You see that the typical size of these blobs, it's large. They are larger in this case, right? That's how you think about this spectrum in Fourier space. On the other hand, if you have alpha b equals to 2, then you are starting to favor, that would be k to the 1, that would be something that's growing. If it's something that's growing, the values of k that are larger, they have a higher weight, and therefore, large k means small scales, and you get this, which seems like a TV, old television static, right? That's pretty much it. So this is more or less how you characterize a turbulent magnetic field. And there is something here, a typical scale, the typical scale of, let's call it granularity, right? Here it's big, here it's small. Things change a lot in a small region. This is what's called a coherence length of this type of magnetic field, which is kind of a stochastic, I'm calling it here, or turbulent, or it's related to turbulent magnetic fields. It's almost the same thing. That's what the coherence length is. It's kind of an average of the spectrum in k-space, more or less. It's just a definition, okay? So the coherence length of magnetic field, it's a very important quantity to characterize what's going on in this magnetic field. There are other things like the helicity. Here it's the magnetic potential vector, A. But this doesn't matter too much for what we are going to do now. And on top of this type of things, it happens naturally in the universe. So we have many environments in the universe that are turbulent. For example, if you take a slice of our galaxy, and you look closely, it's going to be turbulent with spectrum index. Well, in our galaxy, we know that this is close to, I think it's 5/3. I always mess up the definition, so I don't remember the exact number. But it's a Kolmogorov type spectrum. And there is a fixed magnetic field for that, depending on the definition. So yeah, if it's like 5/3 or 2/3, it would be more or less, well, if it's 5/3, then it's positive. If it's 2/3, it's negative. So yeah, it would be something in like, it can be somewhere between. So in our galaxy, we have a specific value of turbulence for the turbulent magnetic field. And in the case of the galactic magnetic field, which is important when we are studying cosmic rays, the component of the galactic magnetic field, it is pretty much this. This is how you define it. This is how you simulate it. This is what you put in the equations when you do it, with a given characteristic alpha b, which depends on the processes going on in the environment. And this determines also how cosmic rays get deflected in the end. We are going to see that a little bit later today. Okay, so this plot, I hope it does help you understand what turbulence is, and especially what the typical coherence scale is, and how this relates with the power spectrum. And yesterday, well, we started with this case, the single particle case. So we had one particle moving in a magnetic field. We did the Lorentz force. We solved all the equations. Yeah, I've shown you this. We defined the Larmor radius, which is the most important quantity, which is the radius of this circle described by the particle here. And then I started doing this. And now I'm just writing down equations so that I don't have to write them at the board to be faster. So once again, we have this definition. We add a perturbation. And of course, I didn't say it before, but the perturbation has to be much smaller. If you take a look here, the absolute value of the perturbation has to be much smaller than this, because otherwise it's not a perturbation, right, if they are comparable. So if you do the same, if you play the same game as what we did yesterday, this was very easy to do. From the Lorentz force, we got these equations, we got these ones. So dv, we got the velocities, we got the positions, and then we have shown that this is true. And now we get the velocities, but now including the perturbation. And then the equations here, they become non-trivial. So things are a bit more tricky to solve. So I'm not going to go into the maths of this, but bottom line is that the motion follows this line, this central line. This central line is what we call the guiding center. The guiding center, it's the line corresponding to what would happen in the homogeneous part of the magnetic field, right? The rest is just the perturbation. We have a guiding center, so the homogeneous magnetic field leads the behavior. And on top of that, we have like these wiggles, this movement, this motion of the particles around that guiding center. And that's what's going on here. So solving these equations, it's non-trivial. And we start to see that the values of delta B, it starts to become important. Things get a bit messy, right? So the motion of a single particle in an inhomogeneous magnetic field, yeah, it starts to get a bit complicated to solve it. So what do we do? Well, since we have this inhomogeneous magnetic field, and since it's turbulent, we have these small perturbations, we can say the following. Okay, instead of working with a single particle in this specific magnetic field, we can use an ensemble of particles all together and study the statistical behavior of everything together, of all these particles in this magnetic field, such that we can calculate averages, we can calculate like statistical properties, which are much easier to do. And with that, well, in order to do that, we need to introduce a few things. I'm not sure if I should go into this derivation, because otherwise you will not have time for other things. Yeah, but okay, let me just briefly outline what I had in mind here. So now, instead of using a single particle in an inhomogeneous magnetic field, we go to an ensemble of particles. And how do we do that? Well, we start using probability distribution functions to do that. And in this case, we have a Gaussian-like behavior with this characteristic D. This D is the so-called diffusion coefficient or diffusion tensor at some point. But the bottom line of this slide is the following. If you do this in one dimension, you'd have this. Okay, let's suppose we have a particle. The particle can move either to the right or to the left, right? And then you can start counting the number of times probabilistically. We can assume that in principle the particle has equal probability of going to the right or to the left in a one-dimensional model. And then we can count the probability that after a given time, the particle did this, let's suppose it did this, then it went like 2 or 3 times, and so on. So we just leave the particle moving, we wait some time, and after some time, the particle is going to be here, for example. So the question that we are asking ourselves now, because we started with the single particle, but now we want to connect with this ensemble of particles. It's what's the probability that we will find this particle at a given distance from the starting position, from the origin. Okay, and I'm going to make the connection with magnetic fields. So this is a random walk type of process. You just count that, and if you solve the equations, you're going to get that the probability, it goes like this. This is a Gaussian, right? You're going to have eventually, if you do this derivation, which I don't have time to do, but if you do this derivation, eventually you're going to get like a Gaussian form. And there is this thing called D, the diffusion coefficient, which is very important because it tells you how fast the particle can explore the surroundings. I find it quite, every time I see a cosmic ray talk, people, especially low energy cosmic rays, people are always talking about diffusion coefficients and so on. And I think it's very hard to get an intuition of what it means. And for those of you working in cosmic rays, or if you have ever been to other schools on Astroparticle, you've seen people talking about diffusion coefficients as if it's something that it's natural, but I find it's a quite complicated concept. But essentially, you should interpret the diffusion coefficient that goes into here as we have a probability, and we have a diffusion coefficient, and the diffusion coefficient tells you how fast the particle can explore its surroundings. An analogy for that would be the following. If you move to a new city and so on, in your first day, I mean, either you are a very excited person or you are more calm. Usually, you explore your neighborhood, your street, your neighborhood, your immediate neighborhood on the first day. Then on the second day, you go a little bit further. On the first week, you're going to go out, you're going to explore a bit farther away. And then after a long time, you're going to explore the whole city, right? The time you take to explore your whole surroundings, your whole neighborhood, your whole city, in this analogy, would be the diffusion coefficient. It tells you how fast you are capable of moving around and exploring the surroundings, okay? And it comes in this analogy. In this case, with this random walk that I just mentioned, of course, this is a very simple, trivial example. But it already captures some of the features. So if the time you take to explore the neighborhoods, or the time the cosmic ray takes to explore the neighborhoods, it's proportional, like the distance that you explore squared, r squared, it's proportional to t, to a given time, to a power. So from this simple case, you get the usual random walk, like 1. This is what we got here in this simple example, okay? Of course, there are other types of diffusions that are constraints. For example, if you were in São Paulo, for example, in this analogy, you would need to take a car, and of course, you are not likely to explore the city on a Tuesday at 8 a.m. because, of course, you're going to get stuck in traffic jam. So that's going to affect how fast you can explore the surroundings, and therefore, the sky is going to change. And you have a few regimes here. So if chi, it's between 0 and 1, you have subdiffusion. If chi, it's between 1 and 2, you have super diffusion. So you have these regimes. And now, we can make the connection between this case of an ensemble of particles with this one. Because we started single particle homogeneous, single particle inhomogeneous. We understood what a turbulent magnetic field is, I hope. And now we are doing ensemble of particles, right? And an ensemble of particles will give us the statistical properties of the motion of a bunch of particles together through an inhomogeneous magnetic field that is characterized by statistical properties. That's a turbulent magnetic field in this case. Because if it was regular, it would be easier to do the calculation. We know how to do that. And then this brings me to a next equation. Okay, don't worry too much about that. Okay, I'm just flashing it here because some of you might be working with this. And then that brings me to something that's called the Fokker-Planck equation, or some variation thereof. The Fokker-Planck equation, it tells you how an ensemble, a collection of individual particles, in this case cosmic rays, described by a function f. This f here, it's usually like the number of cosmic rays in a given volume, for example, so the density of cosmic rays. So how, you can imagine that this is n instead of f, but whatever. It tells you how this density of cosmic rays changes over time and in space. And you can see a few things. So let's suppose that f is not just an arbitrary function, that it's a density. So we have this first term, which tells you, evidently, how the number of particles changes with time. We have this other time, which takes into account the velocity and this mu. This mu, I should define as the pitch as the cosine, in this case, it's the cosine of the scattering angle, and the scattering angle, in this case, it would come from a generalization of these to 2 dimensions. I'm going to generalize only to 2, because I cannot draw in 3 dimensions. So it's the particle moving here, and so on. A generalization of this to 2 dimensions. So the angle at which the particle is interacting with these grid nodes, let's call it theta. It's kind of a scattering, right? Because the particle gets here, there is like, the magnetic field is here. If you take a look, oops. Again, at this plot, so you could have a particle here, so the particle would be moving, and then it would see this very magnetized region. It would interact, be deflected by this magnetized region. And now, what we are seeing is actually, when I say about these scattering centers and this cosine of theta, we are seeing that Fermi acceleration process that we saw on the first day. This is the scattering center of the Fermi acceleration. It's exactly this type of formalism that goes underneath it. Okay, then we have the velocity, the motion here, and there is a dependence on the pitch angle scattering. And I should just say that we have this P here. That's the characteristic pitch angle scattering. I called it phi yesterday, I think, right? Yeah, but it's the same thing. So the cosine of the pitch angle, it gives you mu. And then we have a diffusion tensor in angle, in pitch angle, which can be understood as the degree of tilting here of this curve. So if the curve was just a straight line going up, like there wouldn't be a lot of diffusion in pitch angle. And if that diffusion in pitch angle it's stronger, it does this a lot. So it tilts a lot. Oh, where am I? Here. Okay. I know this part is very mathematical, but I would like to show you the main elements. We also have this diffusion tensor in coordinate space, so x, x, and xy. So it's just because the diffusion tensor, if you just generalize, I start with the one-dimensional example, left, right, but there is also like the up and down, which would be like in this analogy, x, y. And the z component, it's the orientation of the magnetic field, and there isn't much going on. Because of the Lorentz force, it's a vector product. Okay, so that's how we write this equation. So the Fokker-Planck equation and variations thereof tells us how particles, an ensemble of particles move, statistically speaking, in an inhomogeneous magnetic field, or it can also be homogeneous, but this equation works more generally. But we do use it often for the inhomogeneous case or turbulent magnetic fields. And there is this last term, in which you see a dpp. P is the momentum, as you might be thinking. This is momentum diffusion. Momentum diffusion, if you think about it, well, diffusion is a kind of thing that it's changing. Right here, it's in coordinate space. Here, it's in pitch angle space. And here, the momentum diffusion, it's in momentum. So the particle would be changing its momentum. Why? Once again, due to scattering of these irregularities here. So the particle would be moving. It would scatter off these more magnetized regions. For example, the particle would be moving here, and then it would see this blob, then it would move, be deflected in another direction, see this other one, move, and so on. This is, in some sense, the scattering centers from Fermi acceleration that we've seen before. This is what we are talking about now. It all goes into that type of equation. Okay, this is an analytic equation, but it's difficult to solve, so we need numerical methods. To do that, there are a few softwares that do it for you. Okay, and the framework, the theoretical framework, at least the simplest one, that help us treat these problems is the so-called quasi-linear theory. Quasi-linear because, well, you have a perturbation on top. Well, things are usually linear. You just go to first order in the perturbation terms. You know, you do a treatment like this. Actually, with this, the way I started outlining it, you can derive the equations from quasi-linear theory, although it would probably take quite some time. Yeah, so the assumptions that go into here is that we don't have electric fields, which is not true because every particle has its own electric field. However, it's statistically true. If you think about it, in a given medium in the universe, if you take the average of the electric field of a bunch of particles, it's probably 0. Unless, of course, you have something aligning their electric fields. You also assume that the perturbations are small, but I think this is the very definition of perturbations. And then you use the guiding center from the single particle. So essentially, the homogeneous case that is written here at the board. This formalism gives you the guiding center. Then the wiggle room, so the motion around the guiding center. This is the inhomogeneous case of a single particle. And you do this treatment considering an ensemble of particles. And how does this connect now with the magnetic field, the turbulent magnetic field? Remember that the magnetic field is characterized by its K's, right, in Fourier space. It's the same K that goes into here. V, you have the motion of the particle with a given gyro frequency. And there are conditions that we call these resonance conditions. So the frequency, this is an angular frequency. We have the K, once again, from Fourier space, the velocity of the particle, and we have this gyro frequency of the particle. And this n, it's a natural number, which means that you have resonance conditions. If this is a natural number, this can be 0, 1, 2, 3, 4, this number, right? If this happens, you have resonance conditions, and the ensemble of particles starts to show like a collective behavior. So now you don't have just one particle. You have several particles, but they are not disordered. There is some degree of ordering due to this resonance condition. Okay, this is an emergent phenomenon that comes up when you have several particles with their own electric field in a given medium, which is magnetized. Okay, and once again, this K relates to the magnetic power spectrum. The limitations of this quasi-linear theory is that it doesn't work for pitch angles of 90 degrees. Okay, and then there is this thing called the so-called leaky box model. So before I do that, are there questions so far? I mean, I know it's a lot of information. Of course, you cannot get everything, but just an outline of how things are done. Are there questions? Yep. No, I'm not going to do that anymore. I'm stopping that part because I don't want to go to the plasma part. But yes, that's the collective plasma behavior. Yeah. Yeah, you don't use, for example, like if you'd use the Vlasov equation, you'd consider the electric field and so on. You can do that, but in this case, statistically speaking, for what we are doing here for cosmic rays, I think it's okay. Yeah. Mm-hmm. Not statistically speaking. Okay, this is a very strong assumption on a particle-by-particle basis, but I see very few realistic cases in which the average magnetic field of a bunch of particles that just happen to be in a place is non-zero. I think if you take the average of the magnetic field in a given environment, it's going to be 0. I think it's kind of natural because, yeah. So just how do I? If you go to low energies, perhaps. If you go to low energies, that's true. And maybe you don't want to use like the Fokker-Planck equation. You want to use like Vlasov, which is the real plasma equation for that people use. But this assumption, if you're dealing with high energy cosmic rays, especially, it's good enough, I would say. Yeah. And I think the main point here that you can do that is that you have a bunch of particles in a given volume, and then you just calculate the average magnetic field there. I mean, it's very likely that you get something close to 0 compared to the magnetic field that it could have been otherwise, which would be the sum of the individual components. Yep. 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 There are parameterizations, but they usually rely on simulations in the beginning. Because the way to do it is you do the way, okay, if you want to work with the ensemble of particles, you first need to understand the individual particles. So you simulate many, many individual particles and see what happens. Yeah, that's the way I know. I think in the past, probably there was a better way to do it. I'm not sure, because before the computers, right? Because nowadays we can easily simulate, but how did they do it in the 80s or 70s? Because this type of theory, it was developed in the late 70s, early 80s, I think. Yeah. With observations, that's a bit more more complicated because, well, if you go to low energy, it's not that complicated, I think. But at high energies, maybe. I don't know, yeah. But usually, this is done, this is simulation informed. That's how you get the diffusion coefficients. In the past, people did all this analytical work. There are some people who, even to this date, I think they are the last hardcore people who did everything by hand. So they assumed some analytic form for the diffusion coefficient, which now was checked with simulations, with the computational resources available at the time. But not many people do that anymore, to my knowledge. Yeah. Okay, so moving on, once again, the bottom line, I know this seems complicated, but I would be very happy if you could just extract the following information. We know how to deal with individual particles. An ensemble of particles, it's a good approximation in the case in which the magnetic field is stochastic. So we have one distribution of the magnetic field that we can just average over the whole behavior. So this is the bottom line of everything. The concept of diffusion coefficient is also key here. If you understand that, it's already good enough. Also that there are several types of diffusion. Of course, not everything is this toy model that I'm using. And also here, this equation, it's very important. There are several versions of it. Like for galactic cosmic rays now, we are going to use a version of it that's called the convection diffusion equation or advection diffusion equation. People working in solar physics, they use something closely related called the Parker equation, and so on. So this equation, once again, don't worry too much about it, but understand what goes into it, that there are these diffusion coefficients, and these diffusion coefficients here in space, and here in momentum, here in pitch angle, which tells you how things are changing, which quantities are changing. This is the bottom line. And the connection with the Fermi acceleration mechanism, it comes through this term, because this is the scattering of magnetic irregularities shown here, which depends, once again, on the magnetic power spectrum defined in K-space. Okay? Right, so this leaky box model, something interesting, I'm going to do it on the board. I'm actually going to go a bit back before all that. Let me start here because I need a lot of boards. I hope I can do this in 20 minutes to save the last half hour just for more general discussions. Okay, this leaky box model, it's one of the first models to describe the behavior of cosmic rays in our own galaxy, galactic cosmic rays. It was used to describe like cosmic rays up to 10 to the 15 electron volts and so on, or even more. And the model, it goes more or less like this. Our galaxy, to a good approximation, or not so good maybe, it can be approximated as a cylinder. This cylinder has a given radius r of our galaxy, and our galaxy, this is 2h, because our galaxy is symmetric, that's the 2, just to make my life easier. Okay, so the question that we're trying to answer now is how do we connect all these things? So if we have in our galaxy particles moving, diffusing in our galaxy, and let me say one thing before. I've shown you all these equations, okay? I'm not going really to use them now. I'm going to use a very simplified version, but I am going to use the concept of diffusion coefficient. the concept of the diffusion coefficient, once again, how far particles explore the surroundings. And the diffusion coefficient will tell you how far. Let's suppose we have a cosmic ray inside this cylinder. How far the cosmic ray travels on average, or a bunch of cosmic rays travel on average within a given time. That's what we are going to do now. But, okay, yesterday we've seen that cosmic rays, they interact as they travel. There are particle decays, there are particle interactions, many things can go on. And this model, I think it's very nice because it brings together everything that we did during the course. So let me write down a very intuitive equation, and I'm actually going to derive this equation with you now. But it's going to be like an heuristic derivation, okay? It's not very formal, just to get the main elements of what goes into this type of calculation. Let's suppose that we have a density of cosmic rays. I'm going to say that this is n, okay? This n, it can depend on space and time. So we know the continuity equation. This is the continuity equation. Right? So J is the cosmic ray current. So cosmic rays are charged particles, so this is literally like a current density, I should say, at a given position, at a given time. And then, of course, N here, it's the number of particles per volume. And then I'm also going to say that there is a diffusion coefficient in our galaxy. And that's why I did all that development from before. And the diffusion coefficient of our galaxy, it's known. Let's just assume that we know it. And I'm going to assume that it doesn't change with time, because otherwise it becomes too difficult to solve the problem. Okay, so by definition, this part, what I'm writing now, is the part that you should just, okay. This is a bit more complicated, the arguments for that, so I'm going to just tell you that the current, this is the diffusion coefficient. Actually, not the coefficient, it's a tensor. That's why I put this double-headed arrow. Okay, this is a good definition for the current. I actually, to be honest, don't know how to better explain this. Okay, the current, you have the diffusion coefficient, and then the density of particles. This angle that the density of particles, the gradient of the density of particles form with respect to the diffusion tensor, actually. That's why there is this double-headed arrow. And once we know this, we can just rewrite the continuity equation. I'm not going to write these dependencies explicitly anymore. Just assume that except for the diffusion tensor, everything depends on x and t. Okay, this is the part, again, as we say in Portuguese, the jump of the cat. I don't know a good English translation for that. Yeah, you need to put this definition. If you know it, please let me know, but I don't. So, yeah, you need to introduce this, because this is how you connect the diffusion tensor with everything else. And now, okay, there is one thing that quite often happens, which is if you are in a crowd, and I always like to use these crowd analogies because I think this is very useful when you're dealing with ensembles of particles, plasma, and so on. For those of you who are from here or even from other places, if you take the metro at a time like 5, 6 p.m. where everybody is going out, sometimes you cannot really just stand there. Everybody's going to leave, and you're going to be carried together, right? That's something that we call bulk motion. So, yeah, let me write here, bulk. So it's a collective effect. So the whole crowd is carrying you. There is nothing you can do. You're going to be carried by the crowd. And this happens with cosmic rays. So there is bulk motion of cosmic rays, and when we have bulk motion, our time derivative, it changes, right? Because then it's no longer just the time derivative of the individual, of you when leaving the metro. It's the time derivative of course, if you can move, it's your time derivative, but usually there is a time derivative of the whole bunch of particles that are moving with velocity u, and they are carrying you. Okay? So yeah, this is what's the so-called bulk motion, okay? Of the whole collection of particles. And now we are going to replace it, and as I said, this is not a formal definition, I'm just building. And then we are just going to rewrite this equation here using that change. Yeah. Perhaps it's better if I do one thing here instead of writing the whole thing. Sorry. I'm going to introduce something that it's called usually convective derivative. The convective derivative it's this definition here. I'm going to call it this d like that. Okay? The convective derivative, it's the derivative of the crowd. So it's how the motion, if you're not alone, if you're not modeling the system of just one person or one particle, if you're moving a bunch of things together, you use this weird d that I'm calling the convective derivative here. And then we can just replace this in that equation. Right? Okay, we got to this point. This is a good point to consider for now. We have, once again, the convective derivative, which tells you how an ensemble of particles move. And this is also responsible for the motion of a single particle due to the motion of the whole collection of particles of the whole community here. We have this d, which is a diffusion tensor. Right? Why is it a tensor? Because, well, we have magnetic fields, so we might be working in a given coordinate system. And it's a tensor because things have to move different in the x and the y direction and so on. Right? It's a tensor here. Of course, a spatial. This is only space dependent in this case. And now we are going to start modifying this equation. This equation is telling you how the time derivative of the motion of the whole collection of particles. There is a diffusion term. There is a gradient of the number of particles. Okay, but this is telling that everything is zero because we started with the continuity equation, right? But there is no reason for that. We might have a source term added somewhere. We might have a source, an astrophysical source, like a supernova, that just exploded at a given position in our galaxy, at a given time, which is emitting cosmic rays. And this should be added to this equation. So we should add a source term. And the source term we can add to the other side. Okay? And now, also the type of particle that we are dealing with, it matters, especially because we are dealing with collective motion, so protons and electrons, or nuclei, atomic ionized nuclei, and electrons, they don't go together. So I think it's very reasonable to add an A here, this index A, just to indicate the species. So if you're dealing with electrons, with protons, or whatever. So I'm going to do that now. And that's not the same. So if we have a source, we might have one source of electrons and another source for protons, for example. So they don't need to be the same. So it also goes there. Another thing that happens is that now we're describing the motion of a collection of particles in space and time. So what can happen? Think of yesterday. We discussed many types of particle interactions. And the types of particle interactions that we discussed were like interactions with photons or with gas. We briefly mentioned that as well. So interactions would change the density of particles in a given volume, right? Because if we have one particle disappearing and other types of particles appearing, this should be counted by this equation. And so far it's not. So we should add one term that accounts for that. So also, we might have particles that are decaying. So A, for example, might be something that it's unstable, that decays after a given amount of time. So let's start with this decay case. So if we have decay, we know that the typical decay time it's usually proportional to the Lorentz factor times the lifetime of the particle to the -1. Because we are looking at something, once again, we are talking about cosmic rays in our galaxy. This is a toy model that was actually used in the 70s or 80s, I don't remember exactly when. Okay, so this is how particles will decay over time. And, yeah? Yeah, to the -1 here. Ah, yeah, so that's time to the minus. Yeah, so we don't need this. Yeah, sorry. Yeah, I don't need this just for dimensional reasons. Sorry about that, yeah. So since we are looking from here to the frame of the galaxy, there is this gamma, it might be needed. This is the decay time in the rest frame of the particle itself. Okay, so this is what we'd measure. Now there are two situations. First, particle A might be unstable and decay. Second, particle B could decay into particle A and add to this equation. So what I'm going to do is take this equation. I'm going to add to this equation everything that adds particles to the right side, everything that removes particles to the left side. Okay? Eventually. Well, not yet, sorry. Yeah, but I'm going to do that soon. So, but this thing that I just mentioned now, it's very important, this decay time. So I'm going to write down a term that I'm calling this. Formally, it would be a function of momentum, space and time, okay? Formally, because momentum, because there is a gamma factor. And this term, it's going to go into the equation. The equation, once again, it goes with density of particles over time. So I'm writing down this term, and I just want to add this term here to the equation. So it has to have the same dimensions. It has to be compatible. So we have this term for now, and there is a second term, which I just mentioned, which is the conversion of particle B going into particle A. And for dimensional compatibility, I should do that. Okay? So this is the decay, I'm going to call this decay term. And now, there is a second thing that can happen. We can also have, instead of decay, interactions. or scattering. So the scattering, if you think about it, you might have like one particle, one cosmic ray hitting gas, and at some point it might convert into a completely new particle that doesn't exist, especially if you're thinking in nuclear terms, in terms of nuclear physics, or vice versa. There can be a collision of another particle of type, let's say, B, producing ultimately particles of type A. So now we want to write this other term, and it's going to be slightly more complicated. So I'm going to call this now, let's say, chi. Once again, there might be some Lorentz factor dependence, so I'm explicitly writing the momentum. Yeah. So let's consider the following. We might have a case like this. A particle A prime plus B producing A. And this we should write down as a term similar to the K1, a scattering term. And scatterings, as we have seen yesterday, scatterings depend on cross-sections, right? If you remember from yesterday. So now there's going to be a cross-section dependence. So I'm going to write, let me write on the other side because this equation is very long. So the scattering term. Here I have my space, so I want to write down this. So I have to sum over all possible particles that would interact with another type of particle producing this particle of type A, right? Because this is a channel for generation of particles, very logical. Okay, I'm going to write this. I'm going to explain soon what I'm writing. No need for this. Okay. This term here is essentially the cross-section for the process. Yeah, plus other things here, etc. So if you just look dimensionally speaking, density times velocity, velocity is like length over time. This is 1 over length cubed, and this is length squared. So if you multiply everything here, we are getting things that are dimensionally compatible with what we want, ultimately. So this is the differential cross-section for this process, this particular process that's summed over all possible particle B. Okay, so I'm considering one type of particle, and target particles are B. Other, let's say, primary particles that I'm not dealing with now are A prime. So I'm just summing over all possible combinations of what could happen, okay? Because I want to keep modifying that equation until it's in a more useful form. Okay, so with this, I can put everything together. Okay, this is also a bit, I understand this is a bit, I'm just throwing it, but I won't have time, unfortunately, to derive it deeper. But I think the most important thing that I'd like to show you is what goes into this derivation. If you understand just the ingredients and have an idea what depends there, yeah. You're gonna get there, yeah. For now, we don't. Yes and no. The escape is going to be a natural outcome of everything that we are doing. Because yeah, but the leakage is the result. It's not the premise. Yeah, this is the premise, yeah. So the premise is there are sources of cosmic rays in our galaxy. And we are modeling, I'm going to, again, write down the full equation. Now, I know this is very big. Sorry about that. Oops. Yeah. Okay, so we add a source term, the Q that we already had here. Now we go for the decay term. The decay term, or actually not only the decay, but the terms that remove particles. Yeah, I should say that this is not the scattering term. Maybe I can rename it for something more useful. This adds particle, so this is the, yeah, this adds particle to interaction. Okay, and these terms, instead of calling decay term, maybe I can say that this removes particles. Just for clarity. Through interactions, so there is a rate here that particles are decaying, the particles of type A, and there is a rate here that the particles of type B are leading to the production of particles of type A. So that adds things, and here, yeah, but also it's not a good name. What's a good name for that? Or maybe I don't need to name these things. Yeah, do you understand? So if you follow what I'm doing, can you think of a better name for these things? Huh? The source term is the Q here already. So it's like a source term, but not as an astrophysical source, but a particle source and a particle sink term. Yeah, particle source and particle sink, maybe? Yeah. Yeah. There might be one, yeah. Let me see. Where is that? It's on the other side. Yeah, okay. Yeah. No, but you mean this? Okay, I see, yeah. Yeah, maybe there's a minus sign. Yeah, this is removing. This is adding, yeah. This is removing, right? Because this is the particle A decaying. Yes. So I'll put this whole thing on the right-hand side, yeah. So this, yeah, what Claudio said is that there should be a minus sign here, and he's right. So please check if I don't get this, if I didn't get the signs wrong here. So there is a minus sign because, and this minus is very important because it means removing or adding particles. So there is a minus sign here because this is the disappearance of particle of type A due to decay. This is the appearance of particle A. Okay? Now we have this other term. Let me to the density of B particles, yeah, it's somewhere in between the yeah. This term. Yeah, you were right, but if you do the derivation properly, there would be a density of, yeah. So the full way, you were completely right. There is a density of B terms, but this is just the final form of the equation. When you rewrite it, there is this rate of adding particles of type A coming from B. And it's not straightforward because the way you do it, it's something like, let's see, it'd be like, this is actually also, that's why I changed the terms, because this is actually an interaction term that adds things. Yeah. So you would start with something like this, right? And then you could maybe write, this is like 1 over tau BA. I think, yeah, because this would lead to the production through the cross-section of particles that leads to A in the end. But yeah, so this is how you start. Yeah, I'm just skipping some steps, so I don't have this full derivation now. But if you skip these steps, we could do this afterwards. This is not very difficult. Yeah, you would have a density of B, a cross-section, and then this would lead, this would have a rate, but this rate would be due to interactions, not due to decays yet. Yeah, so I'm going to erase this since I'm not 100% sure, so that you don't blame me afterwards. Well, I'm also not sure of anything else, so it doesn't really matter. But now, bottom line here, even if I got one of these signs wrong, what matters is the final one that I want to get right. And so now we are going to have that term. Yeah. And we are going to have this term being added. So this term is leading to the production of particles of type A from the decay of particles of type B. This is a source term. So this would be the disappearance of A to B. Let me say A to B, actually. Yeah, so this becomes a sink term. And then we don't need this anymore. We just change the definition. Okay, yeah, I think this is a more clear way of doing it. So let's go back. I think this was confusing. So once again, this term, this is a sink term, so I'm considering all sink terms here now. I just changed the definition right now, so if you copied it, please write it again, okay? Sink term, particles of type A disappearing due to decay, particles of type A disappearing due to interaction at a given rate. What Pedro just asked now about the density of particles of type B. Yes, it goes into here. I think it would be something like this. And then you'd have a cross-section for the process AB. And based on these definitions, do I have it written? I don't have it written. Yeah. So that, NB and sigma. And what else? And yeah, and the velocity, okay? So Pedro, I think this is your answer. Yeah, this is right. So if I reframe it like that now in a more organized way, so scratch the previous part. In a more organized way, that would be this sink term contains a term that disappears with particle A due to decay and disappears with particle A due to the interactions that lead to the productions of particle B, okay? So this is a sink term due to the interactions. Is that clear? Are you following? This one, yeah, this one would take a cross-section. So this would go into here, ultimately. I'm skipping this step just because what matters is the rate. Yeah. And now, I want this other term, the source term due to interactions, to all processes that lead to the generation of particle A. It can be interactions of A prime with B, or it can be the decay of A prime into A. So now I have a source term. So I think this is more clear. There is no mistake here. And then this sign disappeared. And now, in the final result, I have everything that adds due to interactions in this term chi, which is this one. So particles A prime interacting with B, leading to A. It's in this term. Decay of particle A prime into A, it's also in this term. And I have all sync terms here. Particle A decaying or particle B decaying into A. Interactions of particle A with B disappearing with A. So sync disappears particles, appears particles, minus, plus. Yeah? B into A, yeah, this is this term, yeah, but you can call this B into A. But it doesn't matter how you call it, actually, because it's the sum. No, but then this is actually A prime here. I could write this term separately as B, because the first term here, I'm summing over A prime and B. Everything else decaying into A. So this second term, I just used A prime to be consistent with, so that I don't have to write another summation. Yeah. So everything that decays into A, right? So bottom line, I know this was confusing, sorry about that, but I think you got the idea, right? Main point here, also this is not meant to be a formal derivation. So as long as you understand that we start with the continuity equation, there is nothing popping up out of nowhere. The continuity equation, a density over time, and this gradient. Then we change to this convective derivative. We started adding a source. Then, after we added a source of particles of type A, so we are only dealing with a particle A, then we say, okay, what are all possibilities that will make particle A disappear due to decays or interactions? That goes into this term. Then we say, okay, but there are also channels that produce, due to other interactions, particle A, other interactions of other things in our galaxy may produce particle A. That's what we did here. It could be decays, it could be interactions. Okay? We sum over everything, we put in the same equation, and then we have a final equation. Yep. Questions? No. Mistakes I made? More mistakes? No? Okay, so now, finally, we are going to the leaky box model, because we are going to use this equation. So this equation is sometimes called diffusion convection equation, or sometimes people call it vection. I don't really know the formal difference here, because for me it's the same process. It's called convection because of this change here, which is very tricky, because this change is due to the bulk motion of one particle being carried by the whole of particles. For every part, yes, you got the point. That's why I'm using the index A. So now what we are going to do, we can write this for the main things that we know are in our galaxy. That's the next step. Yeah. I hope so. As usual, I'm too optimistic with time. I always think I'm going to have enough time for that. Well, yeah, I do have to do it in 5 minutes because I had more slides. It took too long. So, okay, now what I'm going to do, now that we have that, I'm going to really simplify this equation. I'm going to say, okay, let's just say that these things here, this is the usual trick, right? When things don't change in an absurd way and so on, you can just say, okay, this time derivative, it's just NA over a typical time scale, TA, and I don't need to solve that derivative. It's just because we want an estimate, an order of magnitude. estimate. And what we are doing now then is we are taking that equation, and I'm saying, okay, the first term, which contains the convective derivative, it's the change, it's Na, so the density of particles of type A. But these particles of type A, they are streaming out of the galaxy. They are leaking out of the galaxy. Then, leaky box model. We have a box, cylindrical box, and the particles are leaking because we have sources producing them in the Milky Way, and these sources are, for example, supernova remnants, other things that could produce cosmic rays. Whatever your favorite source, you can add it to the equation and see if it fits the observations. So the time scale for this, so the density of particles, there is a typical time scale that will be associated to the leakage. This time scale I'm going to call tau-scape. And then we have this QA term, which is the source term. And we have, once again, our sinking terms and our source terms due to interaction. Okay? So this is the simple version of the leaky box model. And then you say, okay, let's really simplify all of that and say that the space and time dependence here, they don't matter too much, that things will, due to the interactions, will only depend on the energy or momentum. You could do that, and then you'd have like a dependence only on the momentum here. And for example, if you assume that cosmic ray sources, they emit particles regardless of where they are in the galaxy, this would depend on P and perhaps T, but not X, right? And you can simplify this a lot. This is how you get to this equation, which brings me to my next point. Okay, I'm going to do part of it, which is some of you might have heard about the boron to carbon ratio in the galaxy. You know, this just seems like empty words for now, but why is this important? Because the boron to carbon ratio, it's an important thing because it tells us about cosmic ray propagation in our galaxy. Even at low energies, okay? This is not exclusive to the high energy part. And I really want to do the odd, like spend 5 minutes with the other thing, so I'm just going to throw the main result here. Sorry about that, but this is explained in many places. You can write these equations for boron and for carbon, and then you're going to have a system of differential equations, right? You just taking these two types of particles. And then, if you do that, you're going to get, yeah. And I'm sorry, I'm not going to derive it. I'm just going to show you the final results. And there are still a few things that I'd like to highlight here. Yeah. So bottom line here is the following. I use this equation, the simplest version of the equation. I applied it to boron and carbon. Here I know that it's assumed, it's implied that I know the lifetimes and everything of all these particles, interactions, and so on. And I can write how much boron do I expect compared to carbon. And this is very important because when you solve this calculation, it's going to give us like a time estimate, for example, for cosmic ray escape from the galaxy. And this time estimate tells us how many sources we should have in our galaxies, because this is where the intuition, the intuition part of physics comes in, because, well, so far it's only equations. Really, even if it's right or wrong, there is a escape. This is the leaky box, so cosmic rays are escaping. But as long as you understand that this escape of particles from the galaxy if we are seeing a lot of cosmic rays in the galaxy, and suppose, like, let's just assume for the sake of argument that our civilization could live for 100,000 years in our galaxy. If we could have data points over 100,000 years, and we could see if there are more or less cosmic rays, we could infer the number of sources, Q, of cosmic rays in our galaxy. So this is very important because it's telling us about cosmic rays in our galaxy, how many sources, and at least at which rate these sources are supplying cosmic rays in our galaxy. Okay? Because this is more or less everything here is related to the rate of escape, hence leaky box model. Everything here is related to the rate of escape of cosmic rays from the galaxy. The galactic magnetic field traps the cosmic rays for some time. We've seen this condition, and then after some time, they might be able to escape, depending on the energy. They might be able to escape or not. But since we know there are cosmic rays in our galaxy, there should be a source of cosmic rays in our galaxy feeding cosmic rays at a given rate, because otherwise we'd never detect these cosmic rays. And that's the whole point of what I just did. Is that clear? Yeah? So I'm running out of time, and I think I did not stress the observations enough because they were always... So my plan for the whole week was to present the theory and then the observations, but I failed miserably. Yeah, I never had time to present the observations, so I'd like just to stress maybe, you know, in 5 minutes, the main things. I think if you got the basics of theory, you understood more or less. From today, I hope you understood what a diffusion coefficient is. I hope you understood the reason for these convection terms, where it comes from, that this is you getting out of the metro at 6 p.m. And everybody, the crowd carrying you out of it. So this is the convective derivative. If you understood all of this and the role of interactions, the importance of cross-sections, even if you don't know how to calculate a cross-section from first principle, but you know how to use it, this is already a very good start, okay? So I do hope you got this idea for cosmic rays in general. And especially for those of you, I know many of you work with neutrinos or gamma rays. Cosmic rays are at the base of everything. As we've seen on the first day, if you have neutrinos, you 99.9% with 99.99% certainty have cosmic rays as their progenitor. For gamma rays, it's also quite often the case that we have cosmic rays. If not, we have electrons, and then it's the same physics that we just described. Same thing. So just going back to this plot, I'm going to do this in 5 minutes, I promise. This I've shown you in the first day. These are the observations. And what we see here, there are a few features in this spectrum. So this spectrum, people think it's a power law. Well, it is similar to a power law with several breaks. And they do an analogy with a leg, a human leg. What you see here at 1 PV more or less, it's the so-called knee. The knee of the cosmic ray spectrum. And what I discussed here, it's more or less everything above the knee, except for this last part, which also applies to low energies. So the knee, it's a small change in the inflection point here. Then there is something at 10 to the 17 electron volts, which is not indicated in this plot, which is the so-called second knee. And then I don't think the leg analogy holds, at least not the human leg. And I was looking for animals with the right type of leg, but I did not find any. And then there is the ankle at more or less 10 to the 18.5 electron volts, 10 to the 18.6. And why are these changes? So every time you see things that are related to a power law, and this power law has breaks, I mean, unless your source it's already broken from start, but phenomenological, suppose you don't know anything about the sources, you are just detecting this. Your theory predicts power laws. So why would you get deviations from power laws? For everything that you are doing, all the messengers here, gamma rays, neutrinos, and so on. Reasonable assumptions. Okay, the sources have the break. Another reasonable assumption. The break comes from some propagation feature. Another reasonable assumption. The break comes from some interaction feature. Right? For example, we discussed the GZK cutoff, which is due to interactions, which cause this suppression. Right? And then we could also imagine that in this case, like, or maybe somewhere else in the universe, the cosmic rays, they are trapped within the source region for a very long time. And then the low energy part, because they have smaller Larmor radii, will never escape. So that would cause a suppression on the other side, on the low energies, right? So every time you see, you expect a power law, but you see breaks, you can explain with these things, or maybe another possibility that I'm not mentioning. But it's usually like sources, interaction, or propagation effects. And you can separate in these classes, and of course, they are not mutually exclusive. Okay, so why am I mentioning this? Because the origin of the knee, what we think today is that the cosmic ray knee here, it's essentially related to the maximal. There are several models, okay, this is not clear, but there is a very convincing model in some sense, which says that this first knee that we see here at 1 PV is due to the maximum energy to which cosmic rays can be accelerated by sources in our galaxies, in our own galaxy, like this. So you can actually use this type of leaky box model like they did 40 years ago or so to infer that the first knee could be the escape of the maximum energy of acceleration of protons. But if you remember, acceleration usually goes with the charge of the particle because these are electromagnetic processes. Therefore, if you have an iron nucleus, iron, for example, it's 26 times the proton, the charge of the proton. So you would expect a corresponding knee if we have galactic iron nuclei at 26 times this energy. And that would be the second knee, which is not shown here, at 10 to the 17 electron volts, more or less. This is quite compelling, in my opinion, but I mean, it could be anything else. There are many ways to get coincidences and features in the right place. And then the next feature would be the ankle. What would the ankle in the cosmic ray spectrum, in this case, be? Now that we have learned about these interactions and propagation, transporting magnetic fields, well, in the past, like until, I think, well, in 2005, more or less, there was this very popular model and very reasonable that started with the assumption that cosmic rays were protons. And if cosmic rays were protons, these would be the GZK cutoff, and you would get, if you remember, we discussed yesterday this, let me write it here, Beth-Heiter preproduction, which is this process. We discussed it yesterday. The ankle here, if cosmic rays were protons, so if you have protons and we consider the CMB as a background, you get something at the energy of the ankle. And you get, if it's protons, you also get something here, like as the GZK cutoff. So yeah, it was a very appealing model. However, later on, the cosmic ray measurements, they have shown that at the highest energies, cosmic rays don't seem to be protons, or at least not dominated by protons. And then we need to come with new models to explain these observations, like the spectral observations. And these new models, I think one that's so-called disappointing model, because, well, it was rather disappointing for people working in the field at this time. They saw that it was not protons. So everything that they were doing would be much more complicated, like the modeling of nuclei and so on. And the disappointing model essentially says that, well, this feature, in particular, the cutoff. The cutoff here, it has to do not with the interaction, like the GZK cutoff that we had before, due to interactions, but rather due to some physics at the sources. It just so happens that the sources of cosmic rays in our galaxy, or in the universe, actually, not in our galaxy, in the universe, don't have enough power to go beyond this maximum energy. So there is no way to extend the spectrum further. So that's kind of the status of the field. There are many sources covering this region here. We have heard in other talks about like things like gamma ray bursts, AGNs, and so on. Many of these sources, they could be responsible for ultra-high energy cosmic rays. They can also populate this region, but the point being that this region here in the spectrum, somehow we don't really know where the galactic sources end and the extragalactic sources start to dominate. That's also one of the main open problems in the field today. We don't even know which type of treatment to do here, because we don't know if the sources are galactic or extragalactic in some energy range in between, right? And I'm out of time, so I'll stop here. Sorry for being late, again.
Questions?
Thank you. It's not really like a question related. I just wanted to thank you for all the lectures. It has been great. And like maybe my question would be if you have some more references, not only on this lecture, but also yesterday's, and if you could recommend some books or things. And
So actually, the way it's done here, I don't have a reference for the way it's done here because this is the way that I understand things. So it's the way that I decided to adopt, even though I didn't do the whole thing. But for example, this type of treatment for the leaky box, there is the Geiser's book. It's called Cosmic Rays and Particle Physics, 2016, Cambridge University Press, I think. Then there is also for Fermi acceleration, although it's also different from what I did here, but it's also a good reference. I like a lot. The Longuer book, High Energy Astrophysics. And these I strongly recommended for everything. For the part about interactions, I don't know a good reference for that. Some people already asked before. I don't really know. For that, maybe some review papers. There is a review paper, by Luis Ancordocchi, I think 2019. Reports in Progress in Physics. It's called Ultra High Energy Cosmic Rays. And for the magnetic field part, there is nothing really organized for that, unfortunately, at least not in the context of cosmic rays, but there is a review by, well, on magnetic fields only, there is a review by myself. It's me and Savelyev, 2021. Yeah, Ulysses was the editor of this special edition. Yeah, but the point being that in these schools, these type of things, there are a few things that are organized, but many things are not. So it's hard to really point to references. But Longuer and Geiser, those are good references in general. Cross-sections in Geiser, yeah. Actually, that's where you should look at cross-sections.
In any case, I think I told you, I asked my students, they are taking notes, to prepare the notes so that we can upload along with the slides. So
I'm going to correct the things in the slides because there are typos. There is a figure that is wrong there. And yeah, then I'm going to give to you the slides.
Good. So you have the slides and the notes taken from this part of the board. Anyone else? Claudio.
Yeah, for the collision terms, well, not in the context of cosmic rays, but in cosmology, you have these Boltzmann equations and something, which is the same collision terms, actually. Yeah. There's a derivation, not very easy to follow, in this book of Kolb and Turner.
Ah, yes. Yes, that's a good one, yeah. Actually, I think I might add that to my next lecture. It's good, yeah. Kolb and Turner. So yeah, it's the derivation. It's in a cosmological context using Boltzmann equations. Right. So it's the density of each species. Yeah, I think I've seen that before. Yeah.
Kolb and Turner.
Yeah, Kolb and Turner, like this. Yeah, it's a book on cosmology. I don't remember the name. I think it's like from
early universe or something.
Yeah, early universe, something. Yeah, yeah. I think it's Chicago University Press publisher.
So my question now. So the magnetic field, I suppose, here is in this D tensor or something, right?
Yep.
Because it gives you the anisotropy or something.
Mm-hmm. Yep. Okay. The magnetic field is the D tensor here. Yeah, that's the connection, because otherwise there would be no magnetic field, but the magnetic field here, it's playing this role of moving the bulk of particles all together.
More questions? No? So let's thank Rafael for all of his lectures. And see you after coffee.
Gracias.